lecture number is 35, and in this lecture I will tell you. Now, we have made enough ground to find out the response, say for example, an RL circuit when it is excited with an impulse voltage x t or V t is equal to delta t. This voltage source V t is equal to delta t. Unit impulse, and unit impulse function in the laboratory you cannot get that. Sinusoidal, square wave, this that you get, but unit impulse you cannot get. But the important is, we will show later that if the circuit is linear and time invariant, then if you know the impulse response, which you will do on pen and paper, then you can predict the performance of the circuit for any other arbitrary input signal. That is why people study this. So, we want to find the impulse response. So, to find the impulse response, that is I want to find out what will be the current I t. And suppose let the initial current in the inductor was some value I 0. So far, we considered excitations to be reasonable functions, and I told you I 0 plus will be equal to I 0 minus. But let us see what happens here. So, let the initial current be I 0 minus, be the initial current, and why I 0 I am writing? Let it be the initial current, let I 0 minus be the initial current. Be the initial current in the inductor, in the circuit, in the inductor. When at t equal to 0, you have impressed an impulse response, that is what? This is your time, t less than 0 minus, current was 0 in the circuit, or not 0, I 0 minus, something was flowing, because it might have inherited from some other circuit some value of the current at t equal to 0 minus. Then suddenly you have connected this inductance and R across an impulse voltage source like this, so much. So, I have applied an impulse voltage here like this. So, this is delta t, this is 0 minus, this is 0 plus, this is equal to your V t applied voltage. Now, I want to know how the current waveform will look like, that is what will be I t. Now, the first thing is I will write down the differential equation, KVL is to be satisfied. So, R I plus L d I d t, I will write it as delta t, that is the voltage applied. But as I told you, delta t on the right hand side, its amplitude is infinitely large. So, you cannot proceed further with this equation. What to do if the right hand side of an equation is infinitely large? Okay. But I know this much, that 0 minus to 0 plus delta t dt is equal to 0, is equal to 1, that is what an unit impulse function is. this is finite. So, better I will transform this equation in this form. So, to do this I multiply both sides by dt, and this will be equal to delta t dt. This I can do, and then I will integrate both sides from 0 minus to 0 plus. Now, why I have integrated like that? Because this quantity on the right hand side becomes finite. This is 1, has to be. Now, let us see what will be the integration of each of these terms. So, this one will be then r integration 0 minus to 0 plus I dt, and this will be like this 0 minus to 0 plus di, and the right hand side is equal to 1. Now, so far as this second term is concerned, this will be equal to, this integral will be I only, and this will be I 0 plus minus I 0 minus. And this side it is equal to 1. Now, the question is, what will be the fate of this integral? There will be some current flowing, and integral of a function, even it has got a step jump, area under this curve when dt is vanishingly small will be 0. Once again I am repeating, there will be some response of the current, it is expected. You have applied something, and I am telling this integral, whatever will be that current waveform, you are trying to calculate I dt as dt becoming vanishingly small. The upper and lower integration limit is the area under this response. Suppose the response of the current is something, I am not sure what it will be, but if any function you integrate between 0 minus to 0 plus, that area will become equal to 0. Got the point? So, this integral will become 0, and then I will say that okay, I 0 plus minus I 0 minus, this has to be equal to 1 by L, or I will tell I 0 plus will be equal to I 0 minus plus 1 by L. Mind you, here is a case where I 0 plus is not equal to I 0 minus, because of the presence of an impulse as an excitation. I 0 plus will be equal to I 0 minus, provided right hand side is not an impulse, that we have learned earlier. But here in this case 0 minus to 0 plus is as small an interval as you can think of. So, current earlier it was I 0 minus 1, in no time, that is at t equal to 0 plus, it will become some value which will be equal to that initial current I 0 minus plus 1 by L. Now, impulse function, some people say it is very simple function, some people say it is simple, but it is disturbing at t equal to 0. Okay, let it disturb at t equal to 0. But you see, for t greater than 0 plus, delta t does not exist. So, this circuit impulse will exist this circuit will be valid for t less than 0 minus to less than 0 plus. Whatever current you want to find out, you can find out, because voltage exists only during this time. But for t greater than 0 plus, for circuit for t greater than 0 plus will look like what? R L, and these two terminals are shorted, no voltage source existing. This you must first understand. This IT now will be an RL circuit with no excitation, because the excitation ceases to exist for t greater than 0 plus. For t less than 0 minus, okay, there was no voltage, but this inductor inherited current from some other circuit, etc. You have put it, that is fine, no problem this side. But for t at t equal to 0, you have applied an impulse, means between 0 minus to 0 plus there exists a infinitely long strip of pulse whose height is infinitely large. That is what delta t is. That is why integral 0 minus to 0 plus delta t dt is equal to 1. So, we started with open mind, KVL is satisfied, Ri plus LdI dt is equal to delta t, that is good. But then the question is, this differential equation I cannot proceed further, simply because right hand side is infinite. But now I exploit the property of impulse function and integrate both the sides in the limit 0 minus to 0 plus. Then the right hand side becomes finite, a bit comfortable situation now, and the left hand side has got two terms. One term is this one, L di. Di, if you integrate, it will be I 0 plus minus I 0 minus into L. And this other term is the integral of the current response over the small time interval. Even the current has a step change, the area under this curve will be 0, because dt is vanishingly small and you are integrating, the value of this function will not matter, delta t make as small as you think of. So, this integral will give you 0, and from this you will get I 0 plus equal to I 0 minus. In other words, what I am telling, think in this way, the inductor had some initial current I 0 minus 1 from some other circuit. Suddenly this inductor is connected at t equal to 0 to this circuit. This inductor has been brought in here after inheriting some current I 0 minus 1, and suddenly you have connected, that is, you have impressed an impulse in this RL network. Then what does the impulse function do? Impulse function changes the current in no time. It was I 0 minus, suddenly the current has a step jump, it is a constant number by a factor of 1 by L. So, it is like a magic wand, impulse touches this, whatever was the initial current, that changes to I 0 minus plus 1 by L. And for t greater than 0 plus, this is the circuit, and this circuit has an initial current I 0 plus. So, to obtain the current for I t for all time t greater than 0, I say that initial current, if it was I 0 minus 1, then in that interval 0 minus to 0 plus, the current will have a step jump 0 minus to 0 plus. What will be the value of the current? Impulse does this one, changes I 0 minus to I 0 plus, that what impulse does, and after that impulse is not there in the circuit, and therefore, the This problem we have solved, an inductor having some initial current shorted. So, response of the current I t, which I am not solving now, will be that initial current into e to the power minus r by L into t. Got the idea? That is, impulse will change the initial current in no time, 0 minus it was, it will suddenly make it 0 plus, and for t greater than 0 plus, oh, circuit is shorted, impulse appeared and it vanished in no time. This is the circuit for t equal to 0 plus. For me, t equal to 0 and t equal to 0 plus are one and the same thing. So, what I will say while sketching this circuit, it was some I 0 minus 1, suppose. I am sorry, I will just show it like this. Oh. Try to understand. This is very interesting. This was suppose I 0 minus 1, inductor current. At this point, this was the current, I 0 minus 1, this was the current. This is as close to the origin as you can think of, I 0 minus. Impulse appears 0 minus to 0 plus. What happens? This current has a step jump. This current jumps to this value at t equal to 0 plus. What is the value of the current? This I 0 minus 1 plus 1 by L. This will be 1 by L. And this is I 0 minus 1, this up to this is I 0 minus 1. So, at t equal to 0 plus current will come here. The moment current comes here, impulse then disappeared and it is a circuit like this. Therefore, current will decay exponentially for t greater than 0 plus. So, at t equal to 0, something happening, it is changing the initial current by certain amount and then it decays down to 0. Understood? Then there is another way of interpreting this result, that is our initial differential equation was like this, L di dt was equal to delta t, is not? This was the initial current. Now, in this equation, the left hand side has to give me an impulse, then only it can balance that impulse. Now, the question is how that impulse can be created. Can the response I be delta t? Suppose I am just arguing from common sense, okay, it is a differential equation, right hand side is delta t, left hand side what it will be. Maybe current has, response of the current is also in the impulse, who knows. If response of the current is impulse, then d dt of delta t, delta dot t will also appear on the left hand side. So, how it can balance the right hand side? Therefore, step change of current has to take place, so that di dt becomes an impulse. That is what it has happened. The response of the current here, response of the current has taken place in the previous. Here is a step jump from this to this by whatever amount that will be caused by this impulse. That is what this equation tells me. Got the point? So, when a circuit is excited by an impulse, it will be like this, and the result is not surprising at all. Okay. We earlier told inductor current cannot be changed instantaneously. That is fine with reasonable functions. That is what the natural things are. But when an impulse voltage, with an impulse voltage, if you excite the circuit which is having an inductance, we now come to know that current can change also instantaneously, almost between 0 minus to 0 plus in no time. In our school days, while studying mechanics, we have learned the term impulse force. For example, if there is a mass, we say that force is equal to m dv dt, is not? If the force is some known functions, reasonable function, we say that velocity cannot change instantaneously, is not? Velocity cannot change instantaneously. That is the rule we apply. V 0 minus equal to V 0 plus. Whatever velocity the mass was moving with, that velocity cannot change instantaneously. Apply a force, okay, velocity will start changing with time, like that. But if you apply an impulse force, velocity will change instantaneously. Example, I suppose somebody is with a bat and I am throwing a ball to him with some known velocity. So, t equal to 0 minus, the velocity was v 0 minus. Then he hits a 6 with all its might, he hits the ball. What will be the contact time between the bat and ball? Very little, no time. But velocity has changed from this 0 minus to 0 plus. Not only its magnitude will change, but also its direction, if you write in vector form. That is the impulse, is not? So, in mechanics also, velocity can change instantaneously in no time practically, if the mass is subjected to an impulse force. What is the nature of the impulse force? The force is very large, contact time is very less, but f into delta t is finite, that is f into delta t. If you bring it here by m is equal to dv. So, between 0 minus to 0 plus, this quantity will be finite, so that a sudden change in velocity can take place. Anyway, so this is the thing. Only thing I will tell you about this thing is that what happens if it is an RLC circuit, second order system. So, suppose I will explain it like this. Suppose you have a second order system d2y dt2 plus. So, in a first order system, how many boundary condition you required? I 0 minus must be known, then only you can solve the circuit. Now, let us consider a second order differential equation, a dy dt plus by. Suppose it is excited by delta t, it could be mechanical, electrical, whatever be the system. Now, it is a second order differential equation, natural response, I know how to solve it. Okay. Now, if this is the forcing function, solution due to forcing function, it will be how it will look like. It will be, you see this circuit, it is a second order system. How many boundary condition I need? I need two boundary condition, y 0 minus I need, and I need dy dt 0 minus. This value must be known, then only I can completely solve the circuit. Okay. This is an impulse function of no help. So, what I will do? I will first multiply this with dt to make it a finite thing delta t. So, multiply both sides by this thing dt to dt plus a dy dt dt plus b y dt, and this side will be delta t dt. Okay. Or this can be also written as d dt of dy dt into dt plus these things are okay. Let me write it clearly so that you understand. Repeat this one b y dt, and this is equal to delta t dt. This will be the thing. Now, I am sorry, this dt has not yet been multiplied, everything I kept, na? I have not, oh, dt I have shown, so correct. dt, yeah, correct. Now, this thing, or I will write it as d of this dt goes here, d of dy dt plus a dy plus b y dt is equal to delta t. Any mistake, point out, this is the thing. Now, as I told you, to make the right hand side some known finite things, I integrate both sides from 0 minus to 0 plus, integrate it. B is constant, so 0 minus to 0 plus, 0 minus to 0 plus, and this is 0 minus to 0 plus. Integrate. What will be the integration of this term? It will be dy dt. Integration will be this thing only, dx x, and it is to be evaluated at 0 plus minus dy dt at 0 minus. This is the first term, this one. This one will be a into y 0 plus minus y 0 minus. This will be this thing, and this integration y dt 0 minus to 0 plus, this will be 0, because it will be some, even if y changes by step, it does not matter, dt is very small. So, functional value of y really does not change, only dt becoming vanishingly small. So, insignificant, 0, and this should be equal to 1 here. So, what are the things I know? I know these two things, y 0 minus and y 0 plus, and dy dt 0 minus, is not? This will be the thing. Acha. One thing you see that, coming back to this equation, right hand side delta t some impulse, left hand side y dy dt d2y dt2. Which of this quantity, is it y, is it dy dt, is it d2y dt2, which of these will have step change, will have step change. Which of these? Can y have a step change, 0 minus to 0 plus? If it step changes, then dy dt will be an impulse, and d2y dt2 will be derivative of that impulse, but there is no delta dot t terms. So, y t cannot be. Can dy dt have a step change? Answer is yes. If dy dt value changes by a step, vertical line, then d2y dt2 will give you that delta which will be perhaps balancing the right hand side delta. So, the question is this dy dt 0 plus and dy dt 0 minus, this term will have a step change. This term will not have a step change, means it will be continuous. Got the idea? Any variable, I suppose it was doing like this is called step change. Dy dt will be something like that. Yt cannot have a step change. So, 0 minus and this is 0 plus, it will be continuous. So, y cannot change. So, y 0 plus will be equal to y 0 minus. It cannot have a step change, simply because if y step changes, then you have delta t as well as delta dot t, right hand side only delta t. How this can happen? So, y 0 plus has to be equal to y 0 minus, and therefore, you must have dy dt, very interesting, minus dy dt 0 minus, this must be equal to 1. So, you have been provided with how many boundary conditions? These two. Now, an impulse comes to this second order system. There was some y 0 minus 1, y 0 plus will not have a step change, it will be a continuous thing. So, I will now calculate y 0 plus, but this dy dt will have a step jump like this. So, dy dt at 0 minus I know. So, I will calculate dy dt 0 plus, I will be able to calculate, will be equal to 1 plus dy dt 0 minus, this I will be able to calculate. And for t greater than, this is what will happen between t equal to 0 minus and 0 plus, these things will happen practically in no time. And for t greater than 0, impulse is not there, right hand side is 0, this is equal to 0 for t greater than 0. Therefore, the same this one is equal to 0 for t greater than 0. So, you will have for t greater than 0 plus, say this will be, the equation will be d2y dt2 plus a dy dt plus b y is equal to 0, and the boundary condition are I 0 plus is known, I will start with this, and not I, dy 0 plus is known, what I am writing, y 0 plus is known is equal to y 0 minus is equal to y 0 minus, because this is given to me, and I will calculate dy dt at 0 plus as 1 plus dy dt 0 minus. So, system will be having no excitation now for t greater than 0 plus, but these are the new boundary conditions. Apply them and solve. Right hand side will be 0. Hope you are following me. We will solve some numerical example later. That is, an impulse whenever it comes, one of the quantities of the differential equation will have an abrupt change, step change. because a step change of a signal if differentiated gives rise to an impulse, that is what we have established earlier. Anyway, thank you.